So in the previous lecture we were discussing about linear momentum conservation. One very important aspect which is very routinely ignored in fluid mechanics is angular momentum, and we talk about angular momentum conservation here. This will be a relatively short discussion. We will discuss about the angular momentum conservation equation, and then we will work out a very representative problem in detail to get the corresponding physical picture. So angular momentum is nothing but the moment of linear momentum. Okay. So the rate of change of angular momentum will be this one for the system. We have to express it in terms of the corresponding terms for the control volume. So this here, what is capital N? So small n is capital N per unit mass, which is R cross B, right. So this is rho is there, rho. Now only one step remains before we come up with an expression. So this is the net rate of change of the moment of linear momentum of a system. So this by definition is what? The resultant moment of everything, including the moment of forces and also couple moment, whatever, resultant moment, say m. This is essentially Newton's second law for angular motion. So we will apply this for a problem where this particular form is applicable. Remember that this particular form is applicable if the control volume itself is not accelerating, otherwise there will be a correction term, right. So this is why there will be a correction term. So just take that you are able to take the ddt inside. So if you have this ddt inside, then it will be r cross dma. Now if this is a small xyz, where small xyz is a rotating reference frame, then that has to be written in terms of a capital XYZ and the a relative, and this is valid only if this is capital XYZ, not small xyz. So with respect to small xyz, if you write this, there has to be a minus correction term, just like what we had for the linear momentum conservation. We will take that up as an alternative method for solving the problem, but let us introduce the problem first. This is the most popular problem of angular momentum in fluid mechanics. This is the problem which is there in all books, no matter how nicely written or badly written the book is, but this problem will be present. So the problem is something like this. There is a water supply and there are a couple of arms and the water enters here and it gets radially spread and comes out like this and it creates an angular motion. In this way water may be spread on the garden and this is called as lawn sprinkler, a very common engineering device. So what is given here is that everything is symmetric and let us say this is a freely rotating device, so that there is no frictional torque here. This length is L, let us call this as also L. The total flow rate is Q, volume flow rate, so this is Q by 2 and this is Q by 2, this is volume flow rate. The area here is A, the area here is A, and this part is very short. This is just to create a bend and change the direction of the flow, because if the water is discharged along this axis there will be no rotational effect. So to create a rotational effect only the direction is altered, but this length is much smaller as compared to this, and remaining there is nothing special about this. You could have large number of such arms, but we are considering these two arms just for our analysis. So first what we will do is we will consider a method 1. Stationary control volume. Then we can write this equation. So let us consider a stationary control volume, maybe half of the domain we take because it is symmetric. So we can take half of the domain. So stationary control volume, if we take, so this is ddt of the system, which is the resultant moment of all whatever forces, couple, etc., is equal to so if you take a small element dV, this is what? This is A dr. At a radial location r, if you take a strip of width dr, so dV is A dr, so we can write r is Ri, so this is unit vector along the x axis, cross, what is V? Velocity of a particle here. velocity of a particle is the velocity of the sprinkler plus velocity of the particle relative to the sprinkler. So velocity of the sprinkler is what? Right, plus velocity of the particle relative to the sprinkler, which is, let us call it Vr. This is due to fluid flow. And then the last term. So we have written this term. I will write this term in a moment and complete the integration. This term I hope you have all of you have followed. This is velocity of the fluid relative to the sprinkler, that is water relative to the sprinkler, how it is flowing. Remember, because it is inertial frame, everything is absolute, we cannot write relative here. So the absolute velocity has to be written, plus integral rho r cross v. So what is r? So this is outflow surface that we are talking about. So its r is Li plus some little bit of amount j, right, cross v. V is then Vr dot eta dA. So we have written r cross v, then Vr dot eta dA. So what is this? It is simply the q by 2, right, the relative flow rate, volume flow rate. Q is the volume flow rate, right. So now let us write all the terms. So first of all, because it is freely rotating, this is 0, null vector. So null equal to so let us write this, this is omega k cross Ri, right. So integral of rho Ri cross k cross I is j, here the j components we can neglect. Yes, one term is missing, which is this one, right. So Vrj, right. So then okay, so this one plus integral of, so we will neglect this small j part, so rho Li, this omega is omega k, right. So omega k cross Li is omega L j and omega k into Vr, omega k cross Vr j is, oh sorry, that is, oh sorry, this is this one. So small board makes it very difficult to write everything. So this is separate, right. So plus Vrj, right. Yes, it is already, so let us forget about the integral because we have already assumed a uniform flow. So this Q has come out as a result of integration only, yes. So then this will be 0 to L, so this so I cross I, this will not matter, but I cross j will matter. So rho r square omega a dr 0 to L k, here both will be k, right, plus rho L omega L plus Vr is q by 2a, right. Right. So you are left with a differential equation which is 0. Here what changes with time? Only omega, right, and r square dr 0 to L is L cube by 3. So rho a L cube by 3 d omega dt plus rho L q square by 4a square plus, sorry, there is another term, so let us write that first, plus rho L square q by 2 omega plus rho L q by 2a or q square by 4a, right. Okay. So this is the governing equation for omega as a function of time. And how do you integrate this? So a simple trick is, this equation is of the form dy dt plus d omega dt plus p omega is equal to q, where this p and q could be functions of time, here not, but in general it could be function of time. So you can use the integrating factor e to the power integral p dt, you multiply both sides. Okay. How do you find out what is the steady state angular velocity? That is very easy. At steady state you will have this equal to 0. Okay. So then you will get the value of omega from here. Of course the direction will be minus, that is it will be clockwise instead of anti-clockwise. So then the next question is that can we solve this problem by assuming that it is a accelerating control volume. So how do we take that into account? So same problem, method 2. that means control volume rotating with the sprinkler. This has to be clearly specified because the drawing wise it is very difficult to distinguish this with the previous case. So then you have the ddt of integral r cross, but this you cannot write as the net torque or sorry net moment of all forces. So this okay. So this is the correction term that we apply in the left hand side, very similar to the rocket problem, but here it is much more complicated because this contains the rotational terms also which need to be clearly evaluated. So let us make an attempt to do that. Okay. So let us start, hopefully we can do it in a very cool head because lots of calculations are there. So left hand side m minus r cross dm is rho a dr a relative. A relative is what? A CV, which is 0 here, there is no translation, only rotation, plus omega cross r plus omega dot cross r plus 2 omega cross Vr. Okay. Right hand side, the unsteady term will be 0. Why? Because the control volume is moving, rotating, and water is also and the water is also the control volume is having a velocity the water is having a velocity v xyz relative to the control volume, because the control volume is moving and the water is moving along with it. So with respect to the control volume there is no net flow. So this is 0, and the last one minus sorry not minus the outflow, the flow term. So rho, so integral of, let us write the last term somewhere here, rho r cross v xyz, right, this is the last term. So integral, so what is this? This is simply with respect to the rotating frame what is coming out. So rho into this integrated is just q by 2. So plus into r cross this. So r is ri plus that little bit of j which is neglected cross Vxyz. Vxyz is q by 2a j, right, this one. This is the velocity at which relative to the sprinkler water is coming out. Okay. So now let us clean it up and see whether we are getting the same final equation as that of the previous method, then only it will be validated that our method is correct. So this is a null vector, so null vector minus this is null vector this term is null, but if it is having acceleration then this term has to be kept, right. Angular acceleration is 0 in this case. I mean if you want you can keep it, in fact you should keep it. You should keep it, I am very sorry, you should keep it. The reason is that although you are not driving it with an angular acceleration, but because omega itself is changing with time, at unsteady state it must have an angular acceleration. So this term must be there, right. So plus omega dot k cross Ri plus 2 omega k cross Vri, right, and the right hand side is rho q by 2 r q by 2a I cross j is k. So let me erase this figure so that I have some space for doing the cross products etc. So this is k cross I is j, so omega r j here also omega dot r j, and here is two omega j, right. Sorry, yes, sorry, Vr is there. Then k cross j is minus I, so minus omega square r I, that I cross I will make this term ineffective. So you have minus integral rho a r dr, I cross j is k, so omega dot r k minus 2 omega Vr integral, one rho is there, right, rho r dr k 0 to L, right. capital A is there. Yes, is equal to rho q square by, this is L, right, not R, right, the name that, yes, this is L, sorry. No, L, I have given the name as L. So rho q square by 4 A into L k. It just requires one more step, 0 to L, 0 to L. So this becomes rho A omega dot L cube by 3, all are multiplied with k, so we can take only the scalar components, minus omega A Vr is q by 2A into r dr is r square by 2, so L square by 2, this is 1, 2, these 2 and these 2 gets cancelled, right. Hopefully these terms are same as the terms in the method 1. So these 2 you bring in the right hand side, the 3 terms and the 3 terms here. This is a painful exercise to do in the class, lots of cross product, dot product, all these things are there. So most teachers tend to avoid this problem and I mean somehow get rid of this and come up with a shortcut way of solving this problem. I suggest that as a teacher do not apply a shortcut to solve this problem, because this is a very representative problem which can demonstrate many things. There can be algebraic issues, I would suggest that you look into it, and like if there is any algebraic issue you let me know, but I would like to emphasize more on the concept, right. I mean while doing all this algebra, something or the other is likely to come up. So instead of taking this algebra as a sanctity, take the concept as a sanctity and try to take it forward from here. Thank you very much for your attention. So we have discussed the control volume analysis for mass, linear momentum and angular momentum conservation. So this is a good time that we start with something which is very common to most types of flows, that is viscous flows. So in the next lecture we will start with the dynamics of viscous flows.